Hello, this is Torcellini at the National Renewable Energy Lab, and today we're going to talk about Advanced Energy Design Guides for both new construction and retrofit, and about a series of guides that can help you design better buildings. Why is buildings energy use so important? Well, it is the largest energy consumer in the United States, taking over 40% of the primary energy consumption. That is larger than the industry sector or the transportation sector. In addition, it uses almost 3/4 of the U.S. electricity and over half of the natural gas produced in this country. When we look at buildings, one way to think about it is the pie is divided roughly into thirds, where buildings take a little bit more than a third. Industry is right at about a third, but one way to think about that is that we live and work in buildings, but industry needs to supply products to those buildings, and we take quite a bit of energy to get people to and from buildings, as well as products and services to those buildings. When we look at the energy used, it's roughly split half and half between residential and commercial. Today we're going to focus on commercial, and as you can see in the graphic, lights, heating, and cooling represent the largest opportunities for energy savings because they are the largest energy consumers. We'll also touch on some of the smaller areas, but we need to remember that the big items to hit are lighting, heating, and cooling. Some of the trends that we see in the commercial sector is that even though energy efficiency is deployed widely in buildings and has advanced greatly over the last 30 years, the commercial building energy growth is still getting larger, and the pie is getting larger. That is because we are building buildings and adding services to those buildings at a rate faster than energy efficiency. In order to change that trend, we really need to think about zero-energy buildings. That is, buildings that can produce as much energy as they consume. As far as making design decisions and operational decisions, every decision that we make has some energy or environmental impact. That's important to remember, as many times we make decisions that we think is just about energy efficiency, but in reality, many, many more decisions are made about buildings that also impact their energy and environmental impact. Buildings are around for a very long period of time, and the decisions that we make today are really mortgaging the energy futures of this country. When we look at making decisions, there are so many ways and so many pathways of making those decisions. This is Isaac, and at the time Isaac was 3, and his father put his puzzle together. And if you look carefully at this puzzle, you notice that it does fit together. However, the pieces are not necessarily in the right spot. It's interesting to me that in putting this puzzle together, that I could put it together such that the pieces were not in their right places. And the 3-year-old was saying, "Daddy, this isn't right." He knew that even though the decision was made to put the pieces together, there was something amiss with it, and they were not in the right spot. Design is about making decisions, and many times we need to make sure we have the right motivation to make the right decision, which leads us to a discussion about who are all the decision makers. Those decision makers are many, many players, from the operators of buildings to the designers of buildings to the occupants of buildings. All these people are making decisions every day. The next question we ask is, what is the potential to save energy in these buildings? When we look at the latest data, we see that buildings use about 90,000 BTUs per square foot. If we took those buildings and leveled them all and rebuilt them according to codes, we could get about a 20% savings. If we then applied a series of maximum technologies, that is, energy efficient strategies to buildings, this could include more insulation, adding daylighting to spaces to get the lights turned off, more efficient lighting, more efficient HVAC, we could cut that number almost in half with today's technology. And a lot of that is about integrating those pieces into the design. If we then took those buildings and added photovoltaics to half of the roof area, across the commercial sector, we could get almost a 90% savings from where we are today. That is a pretty dramatic drop, and even though it's not zero, it is a pretty impressive savings level and really shows what the potential is. Just to show how achievable this was, we looked at several different buildings and saw that their actual energy performance is right around that max tech scenario line. We've seen many, many buildings that have been able to hit energy use intensities that are roughly half what current code is requiring. So how do we do that? The first most important step is to set goals. Measurable goals are always better. If you start with a goal that says, I want a green building, everybody can deliver a green building. And today, there are many, many people who will claim that everything is green. In fact, who would want to be caught creating a black building, a building that is not, respectful of energy resources? But because there's no goal to it, everybody can claim success. U.S. Green Building Council created the LEED rating system as well, and there are other rating systems that are also out there that help set some of these goals, and people can use checklists and other methodologies in order to achieve those ratings. Those are another way of setting goals. Many times they don't hit directly the energy impact, although they are incorporated in those programs. In fact, a better goal might be to design a building to use 30% less energy than ASHRAE 90.1 2013. That really starts to put some numbers on it and start forcing design decisions in order to achieve that energy goal. One of the issues with a goal that is relative such as this is that it depends on a reference building, and that reference building can be highly interpreted, and many different variations of a reference building can be used. In fact, I've seen many times where people spend more time trying to manipulate that reference building than actually trying to save energy in the building. If you create a reference building that uses more energy, then suddenly your building looks better, even though nothing has really changed. What we really want is people to put their effort and time resources into designing buildings that use less energy. Probably one of the better goals out there is to use absolute energy targets, such as 25,000 BTUs per square foot. The concept of a zero energy building also fits into this category, where we're creating a building that will produce as much energy as it consumes. That really fine-tunes the design team to hit both the demand side savings such that renewable energy can make up the difference. All of these are about influencing the decisions that are being made, and in particular, those that are making the purchasing decision, or the owner. Let's talk about adding value to these buildings and some of the concepts that come out of making decisions. If we look at this bar right here in the center, and that represents a typical building that is built today, we can have cost every time we make a design decision. We can either increase the cost or decrease the cost. If we talk about those decisions having energy efficiency impact, we can either save energy or waste energy over here on the left-hand side of the graph. By taking those two philosophies, looking at design decisions having cost impact and energy savings, we can create 4 quadrants. In the upper right, we have quadrant number 1. And that quadrant looks at things that cost money in order to save energy. Well, that's a very traditional view of energy efficiency. That is, in order to save energy, I have to spend more money. That might be on more efficient windows. It might be adding insulation, increasing the efficiency of my heating and cooling system. All come at additional cost. That also yields to calculations that engineers make, such as cost effectiveness, return on investment, other financial tools in order to try to justify the energy efficiency measures that sit here in quadrant 1. Quadrant 2 is very different. This is items that tend to cost money, but also can waste energy. If we look at this, there are several things that could fit into that category. One of my favorites is fountains. And not that I have anything against fountains, but people put in fountains. They clearly cost money, and they also use energy and water. Other examples might be elaborate architecture or atrium, large expanses of glass. All these things can add cost to the project and don't necessarily save energy. The challenge is that many times these types of amenities and or architectural features are not cost justified as part of the project, which leads us to quadrant 3. These are things that can waste energy in order to save money. In fact, many times things that are in quadrant 1, when a project is over budget, slide into quadrant 3 as part of a value engineering process. That is, we've spent too much money and we need to save money. But one of the challenges with that is, and it has kind of forced an attitude about energy efficiency in quadrant 1, is that these become bolt-on technologies. And when we run into a cost issue, we can unbolt them, throw them out of the project, and save cost while wasting energy to come into quadrant 3. These 3 quadrants are very typical of the design industry. Quadrant 1 and 2 are constantly battling for dollars. Do I have more amenities or do I have more energy efficiency? Do I have a better look of my building or do I have energy efficient products? The real challenge and what we want to get people thinking about is what happens down here in quadrant 4. That is, we try to save costs while also saving energy. In fact, as we've done many, many analyses related to this, instead of computer optimization, to allow the computer to make decisions about the envelope, its size, its shape, the amount of glass, the type of heating and cooling system, the computer will always find solutions that fit into quadrant 4. Examples of this might be downsizing the amount of glass, which saves energy, making that glass into daylighting, and then using that daylighting to offset electric lighting, which then reduces the amount of heating and cooling systems that I need. This starts to look at integrated design and putting these pieces together. Most buildings have this cost minimum point where we can save money. But if I'm already committed to spending money along this horizontal line, then I should be willing to get to point 3. Several case studies and analysis have shown that point 3 often sits at about a 50% energy savings for commercial buildings. That represents a value added to the project. That is, trying not to reduce amenities in the building, yet using smart decisions and integrated together to get that value added to get to point 3. So how do we actually implement this in a real building? How do we think about that? How do we look at what that analysis looks like? Well, let's start with one of the harder ones first, because they're buildings that already exist, and that is in retrofitting buildings. The first place of opportunity is to not look at retrofits for energy efficiency in a standalone sense. Let's look at trying to improve buildings as part of other opportunities. Let's say that we need to remodel our building to stiff it up or to reposition the building in the market. Anytime that I'm making a change to a building and making decisions is an opportunity to include energy efficiency. By including energy efficiency as part of other projects, we can start leveraging costs and putting the pieces together. This might include roof, window, skin replacement, and that may be cosmetic. It could also be a failure of those components and they need to be replaced. Another opportunity is nearing the end of life for heating, lighting, or other major pieces of equipment. Perhaps we need to make upgrades to meet codes. That may not necessarily be energy codes, but other codes that are governing life safety or the usability of a building. Other opportunities are when there's refinancing available or new occupants or new owners. It may be a major occupancy change that wants different criteria for their building. These are all opportunities to save energy. In some cases, buildings, as part of repositioning in the market, just want to become greener and as part of a corporate imaging. And that is another opportunity. Another one that drives it more on the energy side are utility incentives. In fact, utility incentives can be leveraged with any of the things that are above. And it may be that the building is just an energy hog, and it is way out of bounds compared with other buildings in the portfolio or other like buildings, and that there is just an incentive. And again, it may be part of a market repositioning that says that it is time to start looking at the building and doing a renovation. For this purpose, we developed a series of Advanced Energy Retrofit Guides tailored very specifically to 5 different building types. These outline some of these strategies, as well as providing analysis, and in some ways you can think of it as being pre-computed energy simulation in order to help provide proven technologies and proven strategies in order to save energy as part of the retrofit process. It really is designed to provide energy managers and owners with comprehensive guidance for planning and executing successful retrofit projects in commercial buildings. We've also tailored the solutions to very specific climate regions, as different climate regions have different solutions and different strategies and different opportunities. It really is an emphasis on how-to guidance. That is, benchmarking the energy use, selecting appropriate financing mechanisms, saving energy immediately by looking at low-cost or no-cost opportunities through commissioning, identifying the best energy-efficient measures to consider depending on the level of retrofit that's being done, looking at whether a building is a good candidate for whole building retrofit, applying integrated design principles as we talked about and leveraging multiple opportunities, developing operation and maintenance procedures to keep everything running as it was intended. Many times buildings were designed with some energy efficiency in mind, but over time those controllers, those pieces of equipment have kind of gotten out of phase with how they were originally designed and are wasting energy. And finally, measuring the progress that we're making towards energy efficiency. Measurement and verification is a critical piece of saving energy and having those energy savings be persistent. The Advanced Energy Retrofit Guides are made up of several pieces, starting with an introduction that is a broad overview of the project, and then moving on to an overview, existing building commissioning, that is low cost and no cost options, to getting more complex with how to plan your retrofit. That then starts to bring in some of the owner and the financial aspects of it. We're showing on this chart the different audiences that match up with each of these different chapters or sections of the book. Measurement and verification, operations and maintenance to keep the building running long term, as well as a conclusion which is applicable to many audiences and provides the motivation on why to move forward. There are 3 categories of efficiency improvement. One is on existing building commissioning. That is those low-cost or no-cost measures that have a quick payback. A stage retrofit, multi-phase series of improvements, may be timed with other planned equipment replacements, as well as whole building retrofits, where the largest opportunities are, as well as opportunities to leverage other needs for retrofit, including remodeling, repurposing, or other major building changes, such as we talked about in the previous slide. This provides the highest level of savings possible. The guide outlines a set of steps that starts in the upper left-hand corner and moves forward. Again, this graphic was taken from the grocery guide, but it applies to other building types, and the information has been tuned for each of those building types. The first step is the plan that we want to do a retrofit and undertake a benchmarking process to see what the savings potential is. If there is a good savings potential, we then go through and audit the building and look for those opportunities. Once we find the opportunities, the $10 question is, how are we going to pay for that? Whether capital is available internally, whether we need to go out and look for other incentives such as utilities and rebates, whether there are other opportunities available such as monies available from tenant sit-outs or other business models. Once we've got the capital, we can look at, do we want to do existing commissioning or take that building through a commissioning process, which is important with everything, or do we want to look at other deeper opportunities, such as the retrofit possibility or the whole building retrofit possibility? This is where the meat of the process happens, and there are sections in the book to talk about each of these. All of them include a measurement and verification process that then can get translated into operation and maintenance to really make the building work as we expect it to work. It is an ongoing process where we might want to revisit this on a frequency interval, say 1 year, if nothing else, just to look at how the building is operating. If you're not measuring it, you really can't figure out what is going on in order to address what the potential is. So that is always the first step. The guide provides examples in several different climates. Those climates are shown here. And it shows examples of what the baseline was in terms of energy efficiency. So you can use these numbers to somewhat gauge what your building might fit, or you can use other tools, such as Portfolio Manager from the Environmental Protection Agency to help with that. Simulations were done looking at typical retrofits that could be done to come up with post-energy use intensity, which is a good metric to start with, as well as the percent reduction. And as you can see here, it is very common to see percent energy savings in the 20 to 30% range. Shifting to new construction, we can look at how do we achieve very aggressive energy savings. When I have a blank slate, it's much easier to make design decisions related to energy efficiency. In cooperation with the American Institute of Architects, the Illuminating Engineering Society, ASHRAE, as well as the U.S. Green Building Council, a series of guides has been put together on both 30% energy savings and 50% energy savings. The first set was on the 30%, and we've since advanced to doing 50% guidance in the new series. Like the retrofit guides, these guidance and recommendations vary by building type and with geographic location. One way to think about these guides is that they are pre-computed solutions to make a building energy efficient. In this case, they have very prescriptive checklists of what to do. If you do everything on the list, you should achieve the level of energy savings that was done. We exhaustively ran energy simulation calculations to show that these energy savings were possible in these different climates. That was then overlaid by a set of experts in each of the individual fields who put together a series of how-to tips, as well as vetting the recommendations to make sure that they would actually be achievable in the field, both from a constructability as well as from a financing perspective. This is really educational guidance. It is not a code, and it is not a standard. In the 30% series, 6 guides have been published, and they are available for a free download. We'll give the website a little bit later in the presentation. They have been largely popular with circulation of over 400,000 copies. It represents a 30% energy savings over ASHRAE 90.1-1999. And even though the standard is now well over a decade old, there's many good tips in the 30% guidance. The 50% guidance was based on a 50% savings from the 2004 version of 90.1. It has achieved circulation of over 100,000 copies, and there have been 4 published, with a grocery guide to be available next spring. How are these projects evaluated? We looked first at creating what we considered a typical building in each of those building types areas. That was overlaid with current standards to make sure that we weren't going to violate any thermal comfort or indoor air quality, or other parameters. We looked at what these buildings would look like based on reference buildings, other support documents, information from the Advanced Energy Design Guide Project Committee, that is that group of experts that was putting this together. Those prototypes got brought together and applied with the 2004 version of 90.1 and modeled in 16 cities to create 16 baseline models. Like the graphic we showed earlier about integrated design and max tech, we applied a number of typical energy strategies to these buildings in each of the 16 cities. The strategies were customized based on the climate location to come up with the low energy model. These solutions were then compared with the baseline and shown to have a 50% energy savings. Much of this information is documented in technical support documents that are companion works to the actual Advanced Energy Design Guide. Those are available online, as well as all of the models that were used for the low energy design cases. So you can take those energy simulation models and tweak them for your own needs. An outline of the Advanced Energy Design Guides shows as follows. First, there's an introduction, how to use this document. Next, we talk about the integrated design process because we know that leveraging opportunities gives us the best energy efficiency. It also integrates the pieces, making it much more cost-effective. Chapter 3 talks about integrating design strategies and how to put these pieces together. What are those technical approaches? Chapter 4 is the meat of the solution. They are tables of design strategies and recommendations by different climate zones. Very specific technical requirements to hit the 50% goal. Each of those has reference points to what we call how-to tips, which provide implementation guidance. Those how-to tips are in Chapter 5. Finally, depending on the guide, we have several appendices talking about different climates, if you want to take it internationally, envelope thermal performance factors, as well as commissioning information. The guides also include sets of case studies, both of schools as well as technologies. Here's an example of one of the case studies that came from the K-12 50% Design Guide. This school, located in Bowling Green, Kentucky, has many different energy efficiency strategies to get it to this advanced level of performance. Several of these strategies have actually been implemented, and you can see here that the energy use intensity for this building is 17,000 BTUs per square foot. That is well below where the targets were from that thermometer graphic that showed the different energy performance levels. You can see some of the strategies that were used on the photographs on the right-hand side, including daylighting in the cafeteria/gymnasium area, as well as daylighting in the classrooms and workspaces. There are also very technology case studies in the guide, such as very specifics on daylighting, as well as variable speed compressors in this case. Just to show what the tables look like in the guide, this one is for one of the northern climates, climate zone 7. This one came from the small to medium office building, and it shows the different components on the left-hand side to make up energy efficiency, as well as then what the recommendation is with links to those how-to tips. There's even a checkbox column on the right-hand side, so as you go through it, you can check the different boxes to show that you're actually meeting the different guidance criteria. It's also examples on how to do different things, such as thermal bridges, as shown in this chart, and appropriate ways of handling that and fixing a typical problem with a solution to get a better thermal envelope. There's also guidance on plug loads. Plug loads typically have been considered unregulated, which also meant that nobody really considered them. But as we start to look at buildings, we've done such a good job at energy efficiency on heating, cooling, and lighting that the plug loads are starting to dominate the energy efficiency problem. Moreover, because of those plug loads, we have to remove heat from the buildings. That adds to the air conditioning load. If we can reduce the plug loads, then we can have many other positive impacts. It's also interesting to note how many plug load decisions are actually made as part of the building design. When we think of what plug loads are, it's not just the things that plug in, as the name would imply, but it really includes everything that is not heating, cooling, ventilation, or lighting. This might include things like the sump pump, elevators, security systems, IT equipment. All of these things are plug loads, as well as the traditional things that you talk about that sit on your desktop, such as computers, perhaps lamps, your telephone, plugging in cellular devices, etc. As a first starting point, one should specify Energy Star equipment. You should also look at eliminating excess equipment. We've seen many office buildings where computer printers get plugged in and never get unplugged even though they're not used. Or fax machines that were once prolific in buildings to an era today where very few people send and receive faxes. The equipment should have the sleep mode enabled, and it should be Energy Star compliant. This is particularly important for things like photocopiers, vending equipment, as well as computer equipment. One way to handle plug loads is to just put them on a time clock or switch control and just de-energize the plug load. We've seen this done in a large scale where after hours, plug loads are just turned off through a central controller. You can also buy plug strip controllers such as the one shown at the right, which do similar things. Kitchen equipment is one that also uses a lot of energy. The guides that are very specific to having kitchens, such as the grocery guide and schools, have special sections in them related to commercial kitchen operations. Commercial refrigeration equipment is also critical, making up over half of the load in grocery stores. But it is also a substantial load in schools and other like buildings that have cooking requirements or food storage requirements. Elevators are also hidden. Many hydraulic elevators require that the oil be maintained at certain temperatures, which is a constant parasitic on the system. And so using regenerative traction elevators is one way to save that energy. In fact, in a regenerative elevator, rather than using electric resistive braking, that energy gets dumped back into the building's electrical grid for use elsewhere. Each section in the back has how-to tips. This is an example in Chapter 5 of service hot water heating, and recommendations and ideas on how to save energy for hot water. An example of many of these pieces being put together in the office environment is NREL's Research Support Facility. This larger scale office building, now at about 360,000 square feet, uses about half the energy of a traditional office building. So that further shows that this level of energy savings is achievable. More importantly, this building was built for very conventional construction budgets in the Denver market. In fact, it's at the lower end of a range of buildings built at the same time. But one of the important pieces that this building needed to attack was looking at plug loads and process loads. If we consider that much of the time a building is unoccupied, in fact, if you consider buildings occupied 40 weeks a year or 52 weeks a year at 40 hours a day or even 50 or 60 hours a day, that only represents about a third of the time. When we started this project, our plug loads were very high. In fact, they used close to the entire design budget of the building. The first technique is to get things turned off during the day and moving that red circle to the left. You can see the numbers drop dramatically, even though we've maintained the occupied power density. we can cut energy consumption in half by managing those plug loads, by getting things to turn off when they're not needed. Design considerations then move the circle, now yellow, up in the graphic. And you can see that the numbers decrease as I decrease the occupied plug load density. What were some of those strategies that were used? That can be used in many, many buildings, whether you're retrofitting or not, or whether it's new or not. These all have substantial impacts to the building. We talked about using elevators that have traction in them, even switching elevator lighting to fluorescent or LED lighting, turning off the elevator lighting when the elevator is unoccupied. In our case, for the office environment, we reduced the number of kitchens in the building. We also eliminated the coolers on the drinking fountain in order to save energy there. What we found is that many people were using the drink coolers where you bring water in, and instead we took that item, which is both producing hot and cold water, and we replaced it with filters on the kitchen sink in order to give a similar quality of water. We also provided ice cubes as well as hot water at the tap for instantaneous hot water. That provided a much more efficient solution for drinking water. We also went to 6-watt LED task lights in all of the office environments. We moved from standard phones to using voice over IP phones, looking very carefully at what the consumption of those phones were. We found headsets at the time that were rated for 2 watts each. This times 1,000 phones does add up. We decreased the number of people using, or number of copiers, fax machines, and printers. And we went to centralized document processing on each wing of the building. In many cases, we reduced substantially the number of machines, and we increased the ability to maintain them because now we're using common parts for all the same machines in these all-in-one machines. And we eliminated all the individual fax machines. As far as computers go, we moved to laptops, which eliminate the need for backup power units at the desktop, as well as being a much more efficient processing system. We found a desktop or a laptop plus a monitor configuration that uses approximately 42 watts. Finally, in our data center, we were using about 65 watts per employee, and we dropped that number to 48 watts per employee by increasing the efficiency of our UPS, as well as moving to blade servers and virtualization in our servers. All these totaled up to a 47% reduction in plug load. These are all things that you can do today. They are outlined in the guides that I brought up. So some final thoughts in wrapping up this seminar. First is set high goals. 50% is not out of reach. And if you set the goal high and you set the budget, then people will strive to meet that expectation. Feel free to communicate back to the lab what experiences you've had. It is possible to submit your case studies and stories to the website shown on the screen. Finally, for more information about the guide, go to buildingdata.energy.gov/CBRD. This is the Commercial Buildings Resource Database. You can do a search on AEDG or AERG for the retrofit guide to get the publications we've talked about today, as well as the support models and the technical support documents. In addition, the guides are available directly from ASHRAE at no cost at ashrae.org/AEDG. For more information on commercial building energy efficiency and modeling, energy modeling, go to openstudio.nrel.gov or commercialbuildings.energy.gov. And thank you for your time today in listening to this session. And I hope that you are successful in your renovation projects and new construction projects to make a substantial difference in how energy is consumed in the built environment.